Welcome, everybody. My name is Victor Reiner. I'm from the University of Minnesota, and it's my great pleasure and honor to introduce our next plenary speaker, Federico Ardila. Federico is somebody whose work I've followed since he got his PhD in 2003 under the same advisor as myself, Richard Stanley at MIT. And I've been watching what he's been doing and paying close attention, throughout his successful postdocs and visiting positions, and he's done great things. And I could talk about his honors. He's had a career award, and most recently has been inducted as a fellow of the AMS. Congratulations. And I want to talk a little bit, though, about how I feel honored and lucky that in combinatorics we have a person like Federico. He has been a tireless advocate for underrepresented groups, and I highly recommend that you read his article in the notices of the AMS in November of 2016 called Todos Cuentan, Cultivating Diversity in Combinatorics. And also, we're just lucky because he has personally produced a pipeline to fantastic Colombian combinatorialists, and I'm eternally grateful to him. So thank you for that, Federico. The greatest honor I can pay to him, though, is I have a Twitter account, I do not tweet, and I don't pay any attention to anybody's tweets except Federico's. So without any further ado, I'd like to introduce to you Federico Ardila, and he'll be talking about algebraic structures on polytopes.
Okay, can everybody hear me okay? So thank you so much for coming. It's a great honor to be here and speak to you. As you might have noticed, I changed the title of the talk a little bit. It's now called Algebraic and Geometric Structures in Combinatorics. And it's a huge honor to be here and also to be introduced by Vic, who has been a friend and a mentor and somebody who has been very influential in my career. So I'm very grateful for that. And I'm also very grateful to finally get this work out. So this is joint work with Marcelo Aguiar from Cornell. And this project has been going on for about 10 years, and we finally managed to get something out written. I don't know if I should call it an article or a book, but it's this preprint Hopf monoids and generalized permutahedra. And like I said, this has taken way too long to get out. Why did we take so long? It's actually really funny. So Erica Clarick, who's a really wonderful writer, did a profile that I really enjoyed reading. And then Wired picked up on it and put this like clickbait name for it. This mathematician lost 5 years of work and reconstructed it all. So that's me, and this is this work. I was kind of embarrassed that all of a sudden this becomes the story of a Colombian that gets robbed in Portland, Oregon. I mean, it really became a story of like me going into the underworld of Oregon, asking all the people, hey, have you seen theorems? Did anybody steal my theorems? And really, I got so frustrated because we really did lose 5 years of work. And this thing sat for another 3 or 4 years until finally, when I was invited to give this talk, I thought this is going to be what I'm going to force myself to talk about this and therefore write about it. So I'm very happy for the opportunity to get this out also. I should say that because this has been 10 years in the works, many other authors have done related work, very beautiful work, and I'm very grateful for all these people who have been in very close communication with us. And we're lucky that I feel very lucky that I'm in a part of mathematics where we collaborate very openly and communicate very openly, and so I'm very grateful to them. They shaped this work as well. So before I tell you about what this talk is about, let me just tell you a little bit of a philosophy of how I see combinatorics. I should say that actually I used to hate combinatorics. It was the field that I really hated the most because I thought it was way too hard. You needed to be way too clever, and I just wasn't that clever, I felt. I was taught that combinatorics was about counting, and to some extent combinatorics is about counting, but not counting in the way that the public thinks about counting, like 1, 2, 3, 4. If I wanted to count let's say the number of chairs in this room, then I'm not going to start going 1, 2, 3, 4. I'm going to look at it and say, okay, I see that there's some structure here. There's some groups. And for example, here in this group, it's a rectangle, so I could count the chairs in this part by multiplying the length times the width, and then so on. So I'm going to use the structure to count. I'm not going to count manually. And in some sense, I think that that's what combinatorics is about. We usually spend a lot of time studying the structure of combinatorial objects, and then as a consequence, sometimes we're able to count them. In my view, when it's a personal taste, I like when we can count things, but I'm more interested in understanding their structure. So the main objective of a lot of my work is to understand the underlying structure of discrete objects. And one thing that I like is that very often that structure is algebraic, that structure is geometric, that structure is topological. And so you end up having connections with a lot of different fields. So let me draw this here. This is a tetrahedron. Because of my bias, I'm a combinatorialist, and so I put combinatorics in the center, but it's a tetrahedron where these four disciplines are really related, and I think that's what this field is about, is the interplay between them, okay? But the reason that I changed the title of my talk is that I realized that this talk is actually centered on the combinatorics. So I'm interested in combinatorial objects, but to understand them, I need to explore their algebraic, their geometric, and their topological structure, okay? So let me begin by telling you how we apply this philosophy in two special cases. So let's talk about permutations. So if I look at the permutations of a set 1 up to n, we know that that set has n factorial permutations. For example, for n equals 3, they're listed there, okay? And okay, that's fine. But like I said, I am less interested in counting them and more interested in what is their structure. So what is the structure of permutations? And so one way of asking that is, what does the space of permutations look like? And this is a philosophy that appears in all kinds of mathematics. So in algebraic geometry, they would call this the moduli space. In topology, they would call it the configuration space. Just what is the space of your objects and how are they kind of related to each other, okay? So for example, with permutations, I don't want to just list them. I want to see which ones are close to each other. And so let me put an edge between two permutations whenever I swap two consecutive numbers, okay? So if I take 1, 2, and 3, and I swap 1 and 2, then I get 2, 1, 3, and I connect those two permutations over there. And when I do that, what I get is this nice hexagon, okay? Now, when I do this for n equals 4, and I'm sorry that maybe this is a little bit harder to read, but these are the 24 permutations of a set of 4 elements. And if I look at which ones are close to each other, and I draw this little graph, it's inevitable, I think, to see that this is not just a graph, this is a polytope, okay? And so this is, in some sense, the birth of this project. It's a very old observation. This polytope is called the permutahedron. It was first defined by Schout in 1911. Then it was rediscovered by Bruhat and Verma in the context of Lie theory. And then Richard Stanley in 1980, I think, really led the combinatorial study of this polytope, okay? So that's one polytope that we're going to be very interested in, the permutahedron. Now, let's talk about a different question, which is the question of associations. So let's say that I have a product of n elements, x1, x2, up to xn, and I ask myself, how many ways are there to carry out this product? And most of us are only able to multiply two things at a time. And so I want to think of how can I take this string and put parentheses around it so that every multiplication is binary, okay? And so for example, for n equals 4, I listed for you the 5 different ways of computing the product A, B, C, D, okay? And again, it's a very nice fact that the number of such associations is this number 1 over n plus 1 times 2n choose n. These are the Catalan numbers, and they're some of the favorite numbers of combinatorialists. They appear in all sorts of places. And I like that enumeration a lot, but I want to dig a little bit deeper and understand not only how many are there, but also how are they related to each other? What is the space of associations, okay? And actually, this is something that I gave to my students in my proofs class. I really believe in, when you welcome people to mathematics, you give them deep things. And so one thing that I asked them is to prove that given the associative law that x times y times z equals x times y times z, and that allows us to say that the product x, y, z is well-defined, I asked them to think about why is the product of 4 things well-defined? Why is A, B, C, D well-defined? In other words, why are those 5 expressions equal to each other? If you only know the associative law, that is an associative law of 3 things. So how do you go from the associative law of 3 things to the associative law of 4 things that says that all of these things are equal to each other. And they sat down and they worked it out, and they came up with a bunch of proofs. But after we compared their proofs, we found that all of them fit into this framework, that these are the 5 ways of parenthesizing. And now I put an edge between 2 of them if there's a single application of the associative law that gets me from one to the other. So let me see if I can point to here. So for example, here I have A times BCD, and between here and here, I'm leaving A fixed and I'm applying the associative law between B, C, and D. And so that's why I connect those to each other, okay? And so this is a proof that these things, that the product A, B, C, D is well defined, okay? But we can't stop there. So they got pretty excited about this, but I told them, okay, well, why don't you do the next one for homework? So we put them in groups of 3. They went home and they did all the ways of parenthesizing 5 things, saw how they were related to each other. And this was the homework that one of the groups turned in, showing the 14 different parenthesizations of 5 things and how they're related to each other. I like this picture a lot. It's a very beautiful picture. It's kind of egg-shaped. I like their design. Actually, these pictures look very different for each group. But when we looked at all the pictures, again, there was one thing that we couldn't help but notice, which is that this thing looks 3-dimensional, okay? And then I joked, maybe somebody should do the next one. Maybe somebody should do the one of 6 elements. There's only 42 parenthesizations, so you should see how they're connected and see what you get. You should get a 4-dimensional polytope, right? So you have to be careful what you joke in class, because one of my students actually did this, and I hope she's here. Christine Alar, I'm going to embarrass you. Can I ask you to raise your hand if you're here? Over there. By the way, she might be applying to your PhD program right now. This was maybe 2 or 3 years ago. So she actually did this, and she made a sculpture of the 42 parenthesizations and put them together and drew this beautiful picture. And actually, I had never seen a picture of the 4-dimensional associahedron, but this is it. And it's a 4-dimensional polytope, except it's drawn on a plane, but it actually is a 4-dimensional object. Okay. This polytope has a very interesting history. This is called people call this the Stashev polytope. So Stashev is a topologist, and he was interested in this object from the point of view of homotopy theory. And actually, there's a really interesting and a little cruel story that Stashev defined this polytope in his PhD thesis, except that he didn't realize it was a polytope. His was curvy, like the one of my middle group over there. And apparently Milner, who was in his thesis committee, showed up at the defense with a sculpture of the 3-dimensional polytope, saying like, dude, it's a polytope. It's not curvy, it's a polytope. If you're in a thesis committee, don't do that. That's but for a long time, people expected that this was a polytope, but nobody could prove it. And finally, Heyman, and I should have put Lee on there also, so gave the first constructions where you actually are able to give coordinates and show that this really is a polytope. Not only does it look like a polytope, it is a polytope. Lodey gave another beautiful construction from the point of view of operad theory, and I'm going to mention that one later. And I want to mention the work of the recent work of my former student Laura Escobar, who also realized that the associahedron, being a polytope, has a torque variety associated to it, and that torque variety has a very natural interpretation as the resolution of singularities of a Schubert variety. So if you're interested, she's around also, and ask her about it. But it's a very natural polytope from a lot of points of view as well, okay? So these are my 2 polytopes, permutahedron, associahedron, and now I want to tell you a story that seems unrelated, but that is related, okay? So the question is about power series. How do you invert power series? Let's say that you have some power series A of x, okay, and it looks like this, and you have a power series, you have A of x, and you want to compute 1 over A of x, the multiplicative inverse. And so you might think, for example, that you know the Taylor series for cosine. Let me see if I can say it off the top of my head. Is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. So given that one, how do you compute the Taylor series of the inverse, which is secant, okay? And you can kind of do this algebraically. You can do the manipulation, and you can find that the coefficients of B are given in terms of the coefficients of A by these formulas over here, okay? And combinatorialists have this urge that whenever we see an integer, we want it to count something. And so one question is, how do we make sense of these numbers? And it turns out that these numbers are precisely telling you what the permutahedron looks like. In other words, the permutahedron knows these numbers. So for example, if you look at the formula for B3, the third coefficient of 1 over a of x, it looks like this. Let me see if I can highlight it. And that's because the third permutahedron is the hexagon, which has 6 vertices, 6 edges, and 1 full-dimensional face. If I look at this next formula, then I'm going to find that the coefficients, the B4 is given by the structure of the next permutahedron, which is this one. It has 24 vertices, that's 4 factorial. It has 36 edges. It has 14 faces, and what's interesting about that is that there's actually 8 hexagons and 6 squares. And they separate into an 8 A3 A1 and a 6 A2 squared. And A3 A1 tells you, well, A3 was a hexagon, okay? So that's why those are hexagons. A2 squared tells you A2 is an edge. When you multiply an edge times an edge, you get a square, okay? And so the point that I'm trying to make with this is that the coefficients of the inverse are exactly given by the faces of the permutahedron, okay? And one implicit thing here is that any face of a permutahedron is a product of permutahedra. And that's implicit in this, okay? Now let's go to a different question, which is, let's do the same, but now for compositional inverses, okay? For example, let's say that I know the series of sine of x, and I think I know that one. It's x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And now I want to compute the compositional inverse, in other words, the coefficients of arc sine, okay? So b of x is the compositional inverse of a, and I want to ask myself, what are the coefficients of b in terms of the coefficients of a? And when you look at these formulas, you get these numbers that look kind of similar. And again, I ask, what do they count? And if you're trained in combinatorics, you start seeing here the numbers 1, 2, 5, 14, and these are the Catalan numbers, and you start seeing there's some nice structure. And it turns out that the story is identical, except that it is now the associahedron that plays this role, okay? So for example, if I look at B3, it tells me that the pentagon has 5 vertices, 5 edges, and the full dimensional thing. Whereas if I look at this next formula, it tells me that this associahedron has 14 vertices, 21 edges, and then it has 9 faces, 6 of which are pentagons and 3 of which are squares, and so on, okay? And so again, the point that I'm trying to make is that now compositional inverses are controlled by the associahedron and its face structure, okay? So in some sense, permutahedra know how to compute multiplicative inverses. Associahedra know how to compute compositional inverses. And I should say that this is not what we were trying to do. We discovered this actually last year after 9 years of working on this project. This just popped out. And we thought, okay, well, everybody must know this. But when we asked the experts, it seemed that this is a new observation, actually, which is that there's this parallel between permutahedra, associahedra, multiplication and composition of power series, okay? And so I want to show you this as motivation to tell you some of the results that we get from this theory that I'm now going to tell you about. So, you know, we built up this architecture over the course of 9 years, and now it's pretty good at just spitting out theorems, and this is one of the things that came out without us looking for it, okay? So we're going to build a bit of abstract architecture, and then I'll tell you a little bit about some of the concrete benefits that we get from that. I'll tell you my bias here. So my co-author Marcelo loves abstraction, and I love concrete things, and it's great that we talk to each other because we push in opposite directions, and we help each other. And so you see there's a very strong abstract component here, and there's also a strong push for trying to get concrete results from this abstraction, okay? So first, I'll tell you about, you know, this is that tetrahedron, and now I would say that in some sense, this is the edge that Marcelo feels most comfortable in. I think that it's fair to say that his work is mostly in combinatorics and algebra, although whenever you do this kind of thing, you can't avoid the whole tetrahedron. So he does geometry, he does topology, but I don't think that he would think I'm misinterpreting him if I would say that this is his main edge, okay? So to tell you about this, I want to tell you about Hopf monoids. Before that, we're going to do a little bit of audience participation. So I just want to ask you to raise your hand if you know, if you feel pretty comfortable with what a Hopf algebra is. And can I ask you to look around? Okay. Can you raise your hand if you know what a Hopf monoid is and you feel comfortable with it? Okay, can I ask you to look around? Okay. Why do I do this? Because I want you to understand that these are not things that everybody in the world knows, and if you're a student that is about to feel like you don't know anything that I'm talking about, I just want you to know that even I barely know what I'm talking about. Let me qualify. I do know what I'm talking about, but I will say that I didn't know any of this stuff before I started this project, and so I really want to try to give you the gentlest introduction possible to this stuff. For those of you that do know Hopf algebras, I think most of you don't know Hopf monoids, and all I'll tell you is that I'm going to talk about Hopf monoids, but there's a functor from Hopf monoids to Hopf algebras. So everything that I say today has a Hopf algebra analogous result. But I want to make the point that in combinatorics, actually, the Hopf monoids are a little bit more useful and actually a little bit simpler. So let me tell you about Hopf monoids, okay? So first I'll tell you, when I say Hopf monoid, what comes to my mind? A Hopf monoid for me is a family of combinatorial structures. So it might be graphs, the family of graphs, the family of posets, the family of matroids, together with two rules. A rule for how do you merge two of your structures into one, and a rule for how do you take one of your structures and split it into two. Okay? So, okay, here's where it gets a little murky. There's not going to be a lot of this. But so how does this work? A Hopf monoid consists of two things. For every finite set, you have a vector space associated to it. And for every partition of that set into two parts, you have two operations, which are the product and the coproduct. Okay? If you like thinking about these kinds of things, then the product just takes, it's a map from the tensor product of h of s and h of t to h of I. And this is just like all products. You take something in S, something in T, and you multiply them. And the coproduct, which might be less familiar to you, is the opposite. A coproduct, you start, the input is one thing, and two things come out. And so it's a map from h of I to the tensor product of h of S and h of T. There's other details that I'm skipping. This is, I'm just trying to get to what's the essence of what I'm doing here. I think we can think more concretely about this. So you should think that you have some combinatorial objects in mind, so maybe graphs, and then h of I is just going to be the span, the formal span of all the objects that are of that form. So for example, an element of h of 3 is going to be a linear combination of graphs on 3 vertices. Okay? This graph plus that graph plus 3 times that graph and so on. And then I find these pictures useful. So a product is a way of taking an object in S and an object in T and merging them. And a coproduct is a way of taking an object in I and splitting it into two. Okay? So combinatorial object with rules to merge and rules to split. I want to mention that all of this stuff is born out of a really wonderful paper of Saj, Nicole, Joni, and Giancarlo Roda, coalgebras and bialgebras and combinatorics. They were the first ones that made this connection between combinatorics and Hopf algebras. And then Marcelo Aguiar and Swapnil Mahajan have a Hopf monoid version of this. Okay? Let me tell you just a tiny bit about the axioms, just because I like these pictures. And they're actually important. So one of the axioms is that multiplication should be associative. So if you have 3 things, and if you want to merge them, then you can either first merge the top 2 and then the bottom 1, or you can either first merge the bottom 2 and then the top 1. Okay? So you can go in this direction or you can go in this direction. And the point is that no matter which way you do it, you should get the same answer. So you can merge 3 things or 4 things or 5 things and so on. Okay? The co-associative law is the dual of that. So it basically says that if I want to split my combinatorial object into 3, there's 2 different ways that I could do that, either going first to the top or first to the bottom, and those 2 should give me the same answer. Okay? So you can split into more than 3 objects, into more than 2 objects, I'm sorry. And then finally, there's the condition that the product and the coproduct should be compatible. And the idea now is that if you have 2 objects and you want to make 2 objects like this, then there's 2 things that you can do. You can either merge them and split them, I'm doing if you want to look up, I'm kind of gesticulating this. So you have two objects. You can either merge them and split them in this way, or you can take each one and split it up, and then merge in the sides. Okay, and so these are the two directions in this arrow. And this basically says that multiplication and co-multiplication are compatible. Okay, so those are the axioms, and they're fun to check with whatever object you have in mind. Okay, so let me show you some examples of how this works. We're going to discuss three examples. The first example is the Hopf monoid of graphs. Okay, so I'm going to consider graphs on a particular vertex set. I'm going to find it useful to allow my graph to have edges and half edges. So for example, here you can see I have an edge joining two elements, but I'm also allowed a half edge that only connects one element. Okay. Now, so I'm considering graphs, and now I have to say, how do you merge graphs? So if I have a graph in my right hand and a graph on my left hand, how do I turn them into a single graph? And I'm going to do the most basic thing possible, which is that I'm just going to let them sit next to each other and not connect at all. So this is the disjoint union of the two graphs. That's the product. Okay? And now, for the coproduct, if I have a graph on a set and I want to split it into two, I'm just going to pull the two parts apart. Okay? There's only one technicality, which is that, so for example, here you can see that I'm pulling apart ABC from DE. The only technicality is that whenever you have edges going between your two parts, they're going to appear in the first part as half edges, and they're not going to appear in the second part. Okay? So you see here the edge AD that was joined between the bottom and the top now becomes a half edge in A and disappears from D. Okay? So this is what's called not co-commutative operation, because I'm not doing the same thing to the left and the right-hand side. So this is the kind of dual version of being commutative. Okay? And then I check that the axioms are satisfied, so I have these three properties to check, and they all check out, and so I have a Hopf monoid of graphs. Okay? Hopf monoid of posets, same thing. If I have two posets, how do I turn them into one? I can just put them side by side and have them not relate to each other. That's the simplest thing possible, and that's what I'm going to do initially. What is the coproduct? Again, I'm going to take my poset and split it into two. Okay, so here I have this poset, and if I split it into A, B, C, D, E, F, G, then A, B, C, and D form its own poset, E, F, and G form its own poset. Okay? But I only do that if the left set is a lower set in my poset. So let me give you another example. If I want to split into A, B, D, E, and C, F, G, then you're going to find that A, B, D, E is not a lower set in my poset because D is bigger than C. And so if the left poset is not below the right poset, then you just send everything to 0. Okay? I need to do that. To be honest, I didn't want to do that, but I tried to check the axioms, and if I didn't do that, the axioms didn't work. And so then this is what the axioms wanted us to do, and so this is what we did. Okay? Hopf monoid of matroids. So can I get a quick show of hands? Who knows what a matroid is? Oh, wow. Matroids are getting more popular. That's exciting. If you know what a matroid is, great. And if you don't, great. So how do I make a Hopf monoid of matroids? Well, let me pretend that I don't know anything about matroids. So I need to invent a way of merging two matroids. So what do? I go look up a book on matroid theory. I open up a section called operations, and I say, how do you join two matroids? There must be something called a direct sum or something like that. And then you look it up, and there is a direct sum of matroids, and so I say, okay, let me try that for my product. And then you need a rule to take a matroid and split it into two. And then again you say, okay, well, how do you go from a bigger matroid to a smaller matroid? And I look up what are the definitions, and then almost every object in mathematics has something called a substructure. And in matroids, it turns out that there's two of them. There's a restriction and there's a contraction. And then you say, okay, well, let me try that. Let me have the coproduct be the restriction to S and the contraction of S. And it turns out that this works. I should say this, these things don't always work, but they work a lot. And these are just three examples, but I want to emphasize that there's actually dozens of examples of Hopf monoids, and there's a lot of structures like this. Okay? And these structures appear in a lot of areas of mathematics. Now, There's another piece of the structure of a Hopf monoid that I haven't described yet, which is called the antipode, and it's a very important part. So Hopf monoids are algebraic objects. Just like in group theory, if you have a group, a very important part of the group is the inverse map. You need to know how to compute inverses to have a group. In Hopf monoids, there is an analogous thing called the antipode, and it plays the role of the inverse. We denote it by S, and just like in groups, the inverse of the inverse is the identity. In Hopf monoids, the antipode of the antipode is the identity. Okay? And there's a definition, and there's a theorem that I'm going to take as my definition because it's the most straightforward way of saying this. So this is the inverse. Okay? It's given by Takeuchi's formula. And in some sense, this is very explicit, and it tells you, okay, every Hopf monoid has an inverse. But there's a big problem here, which is that to compute the inverse, you're summing over all the ways of taking a set and splitting it into smaller sets. And then you run into this phenomenon of combinatorial explosion that this is just too big to do in practice. Okay? This is actually not a feasible formula to apply in practice. And so a general problem is just to find the simplest possible formula for this thing. Because you see that it has signs, and the cancellation is huge, and you need to simplify. Okay? Let me show you some examples for graphs, matroids, and posets. Okay? So this is a picture of a graph, a matroid, and a poset. And I'm not going to pretend that I computed them using Takeuchi, because that would have been awful. For example, for this last formula, Takeuchi would have given me 73 terms. So it's a plus minus sum of 73 terms. But there's a lot of cancellation, and in the end, you just get these 5 terms here. Okay? And this is what happens in general. You have these things that are bigger than exponential, and you want to understand how they collapse into something that's manageable. Okay? That's the question. How do you explain and predict the simplification? And this is something that has been quite hard in the past, actually. There's very few results of this sort. And they're the kind of clever combinatorics that I have come to love it, but it's frustrating when you just see something really clever and you think, well, how do they think of that? And this is how most of these proofs have worked so far. And what we found is an approach that is, you have to invest a little bit more in building up some machinery, but then the theorems just pop out. And so that's what I want to explain. Our approach uses a geometric and topological approach. And then in the end, if you're counting alternating sums of ones and negative ones, one place that appears is actually in Euler's formula for the Euler characteristic of a sphere. It's vertices minus edges plus 2 faces and so on. And it's going to turn out that that's what we're going to use to do these computations. Okay? Just to show you the kind of sad state of affairs of this problem, I think that the only antipode that was known was this one, which has been known for a long time. For all these other problems, until the early parts of this decade, there were some formulas, but they were not the best formula, and they were just too big to apply in practice. Okay, so we kind of didn't really have the clever ideas to compute all these things, and so one goal is going to be a unified approach to compute these. Okay, so just to back up a little bit, I have combinatorial objects. They form an algebraic structure, and now I want to try to understand the antipode of that algebraic structure, which I will show later, sheds light on the combinatorics. It's going to turn out that we're going to go in the other direction and go to geometry now. Okay? And this, I would say, is the edge of that tetrahedron where I live the most. So most of my work lives in this tetrahedron, but is mostly in combinatorics and geometry, and then sometimes I find that I need algebra, sometimes I find that I need topology. And there's a construction that I like very much, which is that of generalized permutahedra. So I'm going to tell you about that one, and that's a different tradition. So in the first tradition, you take a combinatorial object and you make an algebraic object out of it. Here, I'm going to take a combinatorial object and make a geometric object out of it. Okay? So let's start with the standard permutahedron. We already talked about it. We didn't talk about how it's actually a polytope. So we talked about the vertices of this polytope are the permutations, and they literally are. Those are the coordinates. So for example, for n equals 3, I take the 6 permutations of 1, 2, 3, and I just treat them as vectors. They're vectors in 3 space. I take their convex hull, it looks like this. It might confuse you a little bit. I said this was 3-space, so why does it look flat? And there's a reason for that, which is that if you look at all those 6 vectors, they all have the property that the sum of the coordinates is equal to 6. So this is in 3-space, but actually lives on a plane x plus y plus z equals 6. That's why it's actually flat, okay? So that's the permutahedron. And now we're going to consider generalized permutahedra. And here what you do is that you take the permutahedron and you start just moving the facets. You push them, you pull them. But the only rule is that you don't let a facet cross a vertex, okay? A different way of saying this is that you're moving the vertices around. You let them move, but they need to move together in such a way that the edge directions are always fixed, okay? So for example, here I'm taking that hexagon and I'm pushing this face down, and then the bottom edge stays in the same direction at some point. But I might change the combinatorics. I might lose it and make it into a pentagon like you see here, okay? So this is generalized permutahedra. In the optimization literature, these things are known as polymatroids, and they're known to be equivalent to submodular functions. And you might be aware that this is just a huge area of optimization. And one thing that I learned in this project is we really need to listen to people who do optimization. They have a lot to teach us, and we used a lot of what the literature in optimization had to tell us about these, okay? And it also tells you that there's just many, many, many natural generalized permutahedra, okay? In 3 dimensions, here I have the 3-dimensional permutahedron, and then I'll leave that up for a second so that you can start imagining how you might push the faces of the first picture to get the second picture. It's kind of a fun visual exercise. And while you look at that, I'm also going to show you some other pictures to show you that I'm actually going to allow you to push things to infinity and let these things be unbounded, okay? That's going to be important, okay? So these are generalized permutahedra. They're the polytopes that start from the permutahedron and you move facets around, okay? And the way that this project started is that Marcelo and I wanted to build a Hopf monoid of generalized permutahedra, okay? So the vector space part is easy. You know, for each set I, the vector space is the linear combinations of the polytopes in Ri, okay? But the questions that we had to answer is how do you merge polytopes and how do you break polytopes? So if I take 2 of these polytopes, how do I turn them into 1? That's not so clear. And if I take a polytope, how do I break it into 2 according to the partition of I into S and T? That's also not so clear. But then I told you what you do. You go open up the book on polytopes and you say, okay, how do you combine polytopes? And there is a nice operation on polytopes called the product, which is nice because we want a product. And the product is just the Cartesian product. So if you have a polytope in R to the S and a polytope in R to the T, then the product is just going to be the pairs of a point in the first polytope, a point in the second polytope. And that lives in R to the I, okay? And that sounds a little abstract, but it's actually very concrete. For example, a hexagon, which is over here, times a segment, which is over here, is just kind of sweeping the hexagon along the segment, okay? It's a very natural operation. And so we thought, okay, this is so natural that probably that should be our Hopf product, okay? One thing that we needed to show is that if you take 2 generalized permutahedra and you multiply them, then you should get a generalized permutahedron, and then luckily that did work out, okay? Now for the coproduct, this thing was a little bit more subtle, and this is where we actually borrowed from the optimization literature because the polytope literature didn't have anything for us. But we found that if you have one of these generalized permutahedra in R to the I, and if you have a partition of I into S and T, there's something you can do, which is that you can look, so here's my polytope, okay? It's in R to the A, B, C, D. And let's say, for example, that S is equal to A, B, D. Maybe I'll do the green one because it shows better. So S is equal to AD, okay? So what I do is that I look at my polytope, which is right here, and I say, where is the function XA plus XD maximized? And that's what this green arrow is. I hope you can see it. So where is that arrow maximized? And you see that it's in this bottom face, okay? And that face I'm going to call like this. And then there's a wonderful property of generalized permutahedra, which is that when you do that, and you look at that face over there, that face decomposes canonically as a product of 2. And one of them lives in R to the S, and the other one lives in R to the T. And that's exactly what we need. We need to go from R to the I to two things, one in R to the S and one in R to the T. So once we saw that, we thought, okay, if anything is going to work, this is going to work. So this is how we define the Hopf coproduct. And then we have to check the axioms, and these are nice polytope exercises to check. And we found that indeed this satisfies the axioms, and we get that this is a Hopf monoid. Okay? Interestingly, my PhD student Alex Fink, doing something totally different, rediscovered the same result with Harm-Dirksen. And one of the ongoing projects is to understand how these two things are related to each other. I might say a little bit more about that. There's a very recent theorem that we just discovered as I was rushing to get this paper finished so that it would be done before this meeting, which is that actually there's a universality property. So this is the universal Hopf monoid of polytopes with these operations. So if you want to make a Hopf monoid of polytopes in this way, they have to be generalized permutahedra. Okay? And so that's pretty exciting because, at least for us, that was pretty exciting because it actually closes that triangle where we're going from combinatorics to algebra, and these are Hopf monoids, and we're going from combinatorics to geometry through these polytopes. And what we found is that actually there's a correspondence here where these things are actually in bijection in some sense. Okay? So this is the universal Hopf monoid of polytopes. Now, again, if you look at the literature in geometric combinatorics and optimization, as I mentioned, there is a long-standing tradition of taking a combinatorial object and modeling it geometrically. So for example, given a graph, there's something called the graphic zonotope. This was defined by Stanley in '73 in combinatorics. Given a poset, there's something called the poset cone. This was defined by Geisinger in '81 in the literature on order theory, posets. If you start with a matroid, there's a polytope associated to it, which is the matroid polytope. And this was discovered independently in the optimization literature and in the algebraic geometry literature by Edmonds and by Goreski, Gelfand, McPherson, and Serganova. One thing that we noticed, is that actually these three polytopes are generalized permutahedra. But not only that, these maps are actually Hopf maps. Okay, so these maps are actually inclusions of the Hopf monoids of graphs, matroids, and posets into this GP. Okay, so if I want to answer things about G, M, and P, I can just focus on GP, and then all these combinatorial objects live inside there. Okay, and so that's what makes this a powerful object to consider. And then the antipode, it turns out, where for the combinatorial objects it was very hard, actually here the antipode is just incredibly beautiful. It's one of these theorems that is just inevitable to discover. You do examples and it's clear what the answer is. The antipode of a polytope is the polytope minus the codimension 1 faces plus the codimension 2 faces minus. So for example, for a 3-dimensional polytope, the antipode of the polytope is the polytope minus the 2 faces plus the edges minus the vertices. Okay? How do we prove this? I won't say much about the proof except that now we have a geometric context where this very complicated cancellation in Takeuchi has a geometric interpretation as an analytic characteristic of a sphere that actually lives in this generalized permutahedra. Okay? And this is the best possible formula because each term is different. Okay? So there's no possible cancellation. So this is the antipode. And then this closes the tetrahedron because you see that actually we really needed topology to prove this antipode. Okay? Just to show you, so I showed you 3 formulas for graphs, matrices, and posets. And the point that I'm trying to make is that each one of these formulas is controlled by a polytope. Okay? And if you look at the formula on the left, it's exactly telling you what is the phase structure of the polytope on the right. Okay? So you get these theorems pretty automatically. And as a consequence, we were able to just prove all kinds of antipode formulas for all these different combinatorial objects, because it turns out that all of these Hopf monoids on the left that I mentioned at the beginning have models as generalized permutahedra, And this one theorem ends up just proving theorems for each one of these classes, and so we get a lot of nice consequences as a result. Okay? So this is the first result, antipodes. And now I want to try to convince you why this is interesting, if you don't care about Hopf things. And so what I'm going to do is that I'm going to explain to you why this machinery implies the result that I mentioned at the beginning of series inversion. Okay? For that, we need to develop a tiny bit more machinery, which is that Hopf monoids have a notion of a character. Okay? And a character you can think of as just a multiplicative function on your objects. So every object gets a number associated to it, and that association is multiplicative. Okay? So character at s times character at t equals the character at s times t. Now, again, it's part of the general theory that these characters form a group. So the identity is the character that sends the trivial object to 1 and everybody else to 0. The identity is usually pretty trivial. The operation is going to be convolution across the coproduct. Okay, so if I have two characters, character 1 and character 2, and I want to merge them, then I use the coproduct to split into two parts, and I apply the first character to the left, second character to the right. Okay? And it turns out that this is a group with inverse given precisely by the antipode. Okay? So if you want to know the antipode of a character, all you have to do is evaluate that character. Sorry, if you want to know the inverse of a character, you just take the character and evaluate it at the antipode. And this should make tighter what I was saying earlier, that antipodes are like inverses. They really are. Okay? This group is very hard to understand in general because it's very big. Imagine all the multiplicative functions that you can put on objects. That's a huge thing. One thing is clear, which is that if you want to understand it, you need to know how to take inverses, which means that you need to know what the antipode is. Okay? And so we thought, okay, maybe we should see if we understand something about this. But because this is so big, let's try to do it with some simpler Hopf monoids, not all generalized permutahedra. We said, why don't we do it for the two simplest ones that we could think of, which is permutahedra and associahedra. Okay? And let me show you what we got. This was a very pleasant surprise. If you look at the Hopf monoid of permutahedra, so permutahedra live inside generalized permutahedra. Generalized permutahedra are huge. Permutahedra are small. There's one in every dimension. Okay? And if you look at the character group, not of the whole thing, but just the character group on this little piece, it turns out that that character group is isomorphic to the group of power series under multiplication. We thought this was kind of a crazy theorem, at least I did. The proof is not very difficult once you see what the result is. But then the point is that inverting generating functions is calculating inverses in this group. How do you calculate inverses in this group? With the antipode. Which antipode? The antipode of permutahedra. Okay? And that's why if you want to compute multiplicative inverses, they are going to be controlled by the antipode of the permutahedron. Yeah? But we saw that the antipode of the permutahedron is basically the full thing minus its faces plus its edges minus its vertices. Okay? And so that's why you get this formula pretty immediately. Okay? And so you get this as a consequence. Like I said, it was an accident that we discovered this. Now, you can probably imagine what comes next. So when we tried to do this for associahedra, what we found is that, again, if we don't look at all generalized permutahedra, but just at associahedra, which are a Hopf monoid, and if we look at characters on associahedra, we found that the group of characters, that's a typo, that should be the group characters of A of associahedra, is again the group of generating functions, except that now the operation is not multiplication, it's composition. Okay? And for that reason, if you want to invert compositionally, then that's going to be controlled by the antipode of the associahedron. And that's why the numbers that come up in this formula are precisely the phase numbers of the associahedron. Okay? So again, this kind of discovers itself. So it turned out that Lode had asked this question. for the associahedron. So Lode had asked, it would be interesting to find a proof of the Lagrange inversion formula, which is this compositional formula, which involves the topological structure of the associahedron. So again, we read this and we said, it kind of sounds like Lode knew this proof, because what we do is, the way we prove this formula is with the topology of the associahedron. But the one thing that I find even more striking about this is that the associahedron actually has many different polyhedral realizations. There's many constructions of the associahedron. And Lode came up with one of them. And it turns out that it's his associahedron that proves this. So when you apply this theory to his associahedron, then you get the answer to his question. And this is something that Laura Escobar helped me understand. There's many other associahedra, and when you apply this theory to other associahedra, you get something else. And we're trying to understand what you get, but you don't get the answer to his question. So it really feels like Lode understood this very well. And so an ongoing project with Carolina Benedetti, Rafael Gonzalez, Mariel Supina, who is in the room somewhere, is to carry out this computation for other subfamilies of polytopes. Okay? I think I'm going to skip this part and just tell you a little bit about a current direction that we're working on, which I'm excited about, which is that if we look at this formula, you take the antipode of a polytope is the polytope minus the facets plus the codimension 2 faces and so on. It's very tempting to say, okay, look at this, look at the antipode of a pentagon. If you take a pentagon, now delete the edges, okay? And those are the red things that I'm deleting here. Then you basically get the boundary, except that you deleted this vertex too many times, right? Because you deleted it here and you deleted it here, so you should put it back, okay? In other words, if you take the pentagon and you take out the edges and you put the vertices back in, you're going to get exactly the interior of the pentagon, okay? And this is a general theorem that is true in any dimension. You might find it fun to take the cube, take out the square faces, add in the segments, and put out the vertices. You're going to find you get the interior of the cube. And so really, we think that it's inevitable to think that the antipode of a polytope is just the interior of the polytope. And that's a very satisfying way of saying this. And it's also very mysterious then why the antipode squared is the identity. So if the antipode of a polytope is the interior, then why is it that, in some sense, the interior of the interior is the full polytope? And this plays very nicely with something called the polytope algebra of McMullen. And there seem to be a lot of very nice consequences out of this. And it's something that we're exploring with Marcelo Aguiar and with Mario Sanchez, who's a student at Berkeley. Okay? I think that's a good place to stop. So I'll thank you for your attention.
Thank you, Federico. That was fantastic. In order to keep on track, I think we have time for maybe a couple of questions. If you want to ask a question, there are microphones in each aisle, 4 microphones, one in front and back. And are there any questions for Federico?
Yeah, I have a question. If you restrict to the class of generalized permutahedra that are sums of standard simplices, there's a kind of remarkable involution on that set that I think Postnikov was the first to look at, that is like when you have a hypergraph, you kind of take a duality of hypergraphs. Do you have any idea what that does at the level of these Hopf monoids?
Yeah, that's a very good question, and that's actually one of the entries in this table. So if you look at this entry right here, this is what we call the Hopf monoid of hypergraphs, which is equivalent to what you're mentioning. And we do have some results about this Hopf monoid, but actually I don't think that we understand this relation with the Posnikov involution. So I think that's a really interesting question that we should be thinking about. Yeah.
I have a question here. One of the earlier slides, I think you had a coproduct sending something to 0, and I just wouldn't see that in a Hopf algebra.
This one.
Right. So what happens, like when you take the functor from the Hopf monoid to the Hopf algebra, what happens in this setting?
I do think you get 0, but I think maybe this is not the kind of thing that Hopf algebraists are used to doing. But I don't think that is incompatible with the kind of rules of being Hopf algebra. I mean, you do have a Hopf algebra of posets that you get from here, and this is what happens in that.
All right.
Oh no. Okay, sorry. Let me move back. The answer is a little bit different. So in Hopf monoids, the coproduct is that if you take a full set and you split it into 2 pieces, you get something tensor something. To go to the Hopf algebra, what you have to do is now take the sum over all possible partitions of I into 2 pieces. And so what you would do is that some of the terms would be 0, but other ones would not be 0. So
Okay.
yeah.
Yes, that makes a lot of sense.
Yeah.
Thank you.
Thank you.
I wonder if you know if there's any relation of this family of generalized permutahedra with certain deformations of a certain toric variety.
Is Laura Escobar here somewhere? Can I? Okay, so she would be a wonderful person to ask about this. One thing that I do want to say is that a lot of these polytopes have algebraic geometric meanings. I mean, there's moment maps at play, and a key property of generalized permutahedra is that the edges are of the form EI minus EJ, which is very much the kind of thing that you get for moment polytopes, and this kind of...
So is your paper you introduced before, does it talk about this relation to toric variety? I wonder if the proof is sort of an algebraic geometric proof, or does it contain those things, or?
So Laura and Carly Clivens and I are working on trying to make this concrete, because one thing I would say is that for individual generalized permutahedra, there are toric interpretations that are very natural, but we don't have a global interpretation of all of them at the same time that allows us to kind of put the whole Hopf monoid structure in there. So it is something that we're thinking about and that I think should work out, but we don't really have concrete theorems on how this toric point of view relates to the Hopf point of view.
So I think having such a nice algebraic structure, I think this is somehow phenomena coming from a certain algebraic geometric fact. Could it be? I wonder if you have some ideas. Like there's like wall crossing of some tropical structure related to this algebraic structure.
Let's talk afterwards, because I am very excited about that kind of thing, and I have some speculations, but nothing that I would dare say over the over the microphone in front of everybody, and with the risk of being wrong.
And I think in the interests of keeping things going and preparing for the next lecture, let's thank Federico one more time.